A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
My Weird Prompts is a community-driven initiative exploring how AI can fuel curiosity and uncover the fascinating ways our world works. GPU compute for this podcast is generously provided by Modal. Learn more at modal.com.
Have you noticed that the digital sandwich is finally starting to feel like a relic of the past? You know exactly what I am talking about. It is that awkward, mid-2020s posture where you are holding your phone horizontally like a slice of pizza, shouting into the bottom of it, and then staring intensely at a frozen cursor or a bouncing colorful bubble while you wait for the cloud to figure out what you just said. It was this weird performative ritual we all did because we knew the machine was slightly behind us. It feels like we are finally moving into an era where the machine just hears us in real time, without the awkward pause, without the sandwich, and without the frustration.
It is a massive shift, Corn. Herman Poppleberry here, and I have been diving into the research from just the last couple of weeks. We are seeing this fundamental collapse between the speed of thought and the speed of the machine. For years, we accepted that there was a latency tax on intelligence. If you wanted the AI to be smart, you had to wait. If you wanted it to be fast, it was going to be a bit of a dunce. But today's prompt from Daniel is about the three pillars of modern automatic speech recognition architectures, specifically how things like Connectionist Temporal Classification, Encoder-Decoder models, and transducers are evolving in March 2026 to finally kill that latency gap once and for all.
I like that we're calling it the pillars. It makes it sound very architectural and sturdy, which is a nice change from the brittle voice systems we used to deal with. Daniel wants us to look at how these three different ways of building a brain that hears are actually converging. Because for a long time, you really did have to choose your fighter. You could have a fast model that was essentially a high-speed phonetic typewriter, or a very smart model that took 10 seconds to reply, because it was busy contemplating the deep context of your sentence.
That is the classic trade-off that has defined the industry for a decade. We used to talk about word error rate, or WERR, as the only metric that mattered. If a model got 95% of the words right, we called it a success. But as of this month, the industry is pivoting hard towards something called Semantic Word Error Rate. It is a much more sophisticated way of looking at the problem. It is not just about whether the model got every thud and A correct. It is about whether the meaning is preserved for the large language model that is sitting downstream. If you are building an autonomous agent, you do not care if the transcription is verbatim, perfect as long as the intent is captured within 200 milliseconds.
200 milliseconds is that magic number, right? That is the human conversational threshold. Anything slower than that, and we start to feel that uncanny valley of lag, where the conversation starts to feel like a long-distance satellite call from the 1980s. So, let us break this down for the folks who are trying to keep up with the technical shifts. If we are looking at these three pillars, CTC, encoder, decoder, and transducers, where does the speed come from? I know Connectionist Temporal Classification, or CTC, has always been the one people point to when they want raw throughput.
CTC is still the speed king, no question about it. If you look at the Hugging Face Open Automatic Speech Recognition leaderboard right now, models like NVIDIA's Parakeet-CTC are hitting real-time factor scores exceeding 2,000. To put that in perspective for the listeners, that means the model can process 2,000 seconds of audio in a single second of compute time. It is essentially a fire hose of transcription. You could feed it an entire day's worth of audio, and it would finish transcribing it before you could finish a sip of coffee. The reason it is so fast is because of something called conditional independence.
Conditional independence sounds like a fancy way of saying the model has a very short memory, or maybe no memory at all.
In a way, yes. It is a very live-in-the-moment architecture. When a CTC model looks at a frame of audio, usually a tiny slice of about 10 to 30 milliseconds, it makes a prediction about what sound that is without looking at what it predicted for the previous frame. It treats every slice of audio as its own little island. This was a massive breakthrough when Alex Graves introduced it back in 2006 because it solved the alignment problem. Before CTC, you had to manually tell the model exactly which millisecond corresponded to which letter. CTC allowed the model to map audio to text, even if the timing was not perfectly synced up by using a blank token to fill the gaps. But because it lacks that internal language model, because it is not looking at the words around it, it makes silly mistakes. It might hear the sound for and have no idea if it should be the number for or the preposition for.
So it is like a very fast court reporter who is typing phonetically at 300 words per minute, but has no idea what the trial is actually about. You get the text instantly, but you might need a human or a second AI pass to make it readable.
Which is why for years, people had to bolt an external language model onto CTC systems to clean them up. You would have the CTC model do the hearing and then a separate n-gram model or a transformer do the correcting. But in 2026, we are seeing that the sheer throughput of Parakeet-CTC is so high that developers are using it for things like live captioning for massive sporting events or global conferences. In those cases, a 2% higher error rate is an acceptable trade-off for getting the words on the screen before the speaker even finishes their sentence. However, if you want deep understanding, if you want the context king, you have to look at the second pillar, which is the encoder-decoder architecture.
This is the territory where Whisper lives, right? This is the architecture that changed everything a few years ago. This is where the model actually sits down, listens to the whole story, and then tells you what happened.
That is the core mechanism. Models like OpenAI's Whisper use an attention mechanism to look at the entire audio sequence at once. Think of it like this. The encoder side creates this rich, high-dimensional representation of the audio. It is capturing the tone, the background noise, the accent, everything. Then the decoder side generates the text one token at a time, but it can look back at everything the encoder found. Because it sees the whole context, it almost never makes those for versus for mistakes. It knows the grammar, it knows the flow, and it can even handle multiple languages or heavy background noise better than almost anything else.
But the waiting part is the killer for the user experience. If I have to wait for the encoder to process a 30-second clip before the decoder even starts talking, I am right back in the digital sandwich. I am standing there waiting for the machine to finish its homework. This is why Whisper, as great as it is, always felt like a batch tool rather than a live tool.
That has been the traditional limitation, but the developments from earlier this month are actually starting to bridge that gap in a way that is frankly mind-blowing. On March 11, 2026, researchers at Alibaba published a framework called Uni-ASR. It is a unified large language model-based system that allows a single encoder-decoder architecture to switch between streaming and non-streaming modes. They found a way to use something called block-based attention. Instead of waiting for the whole 30 seconds, the model processes small blocks of audio and starts decoding, while the encoding of the next block is still happening in the background. It is a bit like a relay race where the second runner starts moving before the baton is even handed over.
I saw that Microsoft also dropped something huge on March 16th. They called it Vibe Voice, ASR. And the claim there was that it could handle 60 minutes of audio in a single forward pass. That seems like a massive leap in memory efficiency for an attention-based model. Usually, those things choke if you give them more than a few minutes.
It is a breakthrough in how we handle long-form audio. Usually, with attention-based models, the computational cost grows quadratically with the length of the audio. If you double the audio length, you quadruple the work. But Vibe Voice seems to be using a more efficient state space approach or a highly optimized chunking mechanism that allows it to keep a global understanding of a 1-hour conversation. It can do the transcription, the diarization, which is identifying who is speaking, and the timestamps all in one go. It is essentially a one-and-done model for long-form content.
It is impressive, but I still wonder about the always-on use case. If I am talking to a pair of smart glasses or a robotic assistant in my kitchen, I do not want a unified framework that is trying to be two things at once. I want a specialist that is built for streaming from the ground up. And that brings us to the third pillar, the transducers. I know you have been obsessed with the Token-and-Duration Transducer lately.
The transducer, or RNNT, is really the unsung hero of the AI world. If you use Alexa or Siri, you are using a transducer. It was also pioneered by Alex Graves back in 2012, and it is designed from the ground up to be a streaming engine. Unlike CTC, it has a predictor module, which is basically a mini language model built right into the architecture, so it has a memory. It knows that if it just heard "I would like," the next word is probably to or a. It is conditionally dependent, which makes it much smarter than CTC while still being able to output text character by character as you speak. It does not wait for a block or a clip. It just flows.
So why hasn't it taken over the world? If it is smart and it is fast, why are we still talking about the other two? Is it just a matter of complexity?
It is computationally expensive and notoriously difficult to train. You have this joiner component that has to reconcile the audio features from the encoder and the text features from the predictor. Imagine trying to merge two high-speed highways into a single lane that is the joiner. It creates a massive bottleneck. But that is where the Token-and-Duration Transducer, or TDT, comes in. This is the big news from NVIDIA's GTC conference on March 19th.
Explain the duration part of TDT, because that seems to be the secret sauce that everyone in the dev community is talking about this month.
In a standard transducer, the model has to process every single frame of audio, even the silences, the ums, or the redundant parts of a long vowel sound. It is constantly asking, is there a new word here? No. How about now? No. It wastes a huge amount of energy and compute on blank frames. TDT changes the game by predicting not just the token, but how long that token lasts. It says, the word hello starts now, and it is going to last for the next 15 frames, so I'm going to skip ahead and not even look at those 15 frames.
Oh, so it is basically an efficiency hack. It is like skipping the boring parts of a movie because you already know what happens in the next 3 minutes. It is just jumping to the next meaningful event.
That is exactly the logic. By skipping those redundant frames, NVIDIA's Parakeet-CTC 0.6 billion version 2 model, which just came out on March 12th, is 64% faster than a standard RNNT model. And the crazy part is that it is actually more accurate. By focusing only on the meaningful transitions in the audio, it reduces the noise that the model has to deal with. Jensen Huang was on stage at GTC highlighting how this is being baked into the Nemotron 3 suite. They are targeting glass-to-glass, latency of under 250 milliseconds.
Glass to glass being the time from when the sound hits the microphone glass to when the response appears on the screen or comes out of the speaker. That is the gold standard. But Herman, what about these speech-augmented language models, or SAMs? I have been seeing Canary Quen 2.5 billion popping up all over the leaderboards. Is that a transducer, or is it something else?
Canary Quen is more of a hybrid, leaning toward the encoder-decoder side, but with massive scale. It was released in January, and it has already pushed Whisper version 3 out of the top spot on the Open ASR leaderboard with a 5.63% average word error rate. What makes these SAMs different is that they are not just transcription models. They are large language models that have been taught to hear. They treat audio tokens just like text tokens. They are essentially multimodal from birth.
So instead of having a hearing model that talks to a thinking model, the thinking model just has ears. We are removing the middleman.
That is the ultimate goal of the unified era. We are moving away from the modular pipeline where you have an ASR model, then a translation model, then an LLM, and then a text-to-speech model. That pipeline approach is where all the latency lives. Every time you hand off data from one model to another, you lose time. You lose 50 milliseconds here, 80 milliseconds there, and suddenly you are back to the digital sandwich.
That brings us to Qt and their Moshi model. I have been reading about this French lab, and they seem to be taking a completely different path. They are talking about full duplex spoken language models.
Moshi is fascinating because it effectively bypasses the traditional speech-to-text pipeline entirely. It operates on audio latents. It is not transcribing your words into text and then thinking about them. It is responding to the sound of your voice with the sound of its own voice. They are hitting 160 milliseconds of latency. That is faster than some human reaction times. You can interrupt it, you can laugh with it, and it responds to the prosody, the emotion and rhythm of your speech, not just the words.
That sounds incredible for a companion or a game character. But does it actually work for business use cases? If I am a doctor and I need a transcript of a patient visit, or I am a lawyer and I need a deposition, a model that just vibe checks the audio and talks back isn't going to give me the document I need.
You are hitting on the big controversy of March 2026. There is a growing divide between generative voice and analytical ASR. If you need a perfect, searchable, legally defensible transcript, you are still going to use a model like Microsoft's Vibe Voice or a high-end SAM like Canary Quinn. These models are being trained using OpenAI's GPT-4o transcription as a teacher model. Even though Whisper is the open source flagship, everyone in the industry knows that GPT-4o's internal transcription is the gold standard for accuracy, so researchers are using it to distill smaller, faster models. They are essentially teaching the small models to hear, as well as the giant models.
It is funny how GPT-4o has become the professor for all these smaller models. But let us go back to that semantic word error rate you mentioned. Why is that becoming the new standard? Is it just a way for companies to hide the fact that their models still make mistakes?
No, it is actually a more honest way to measure performance in the age of agents. If a model transcribes I think we should go to the store as we should go to the store, a traditional word error rate metric would penalize it heavily for missing all those filler words. But a semantic word error rate metric would give it a perfect score because the meaning is identical. More importantly, it focuses on critical errors. If a model transcribes a drug dosage as 50 milligrams instead of 15 milligrams, a traditional metric sees that as a one-letter error. A semantic metric sees that as a catastrophic failure. It is about prioritizing the information that actually matters for the task at hand.
That makes total sense. We are optimizing for the end goal, not just the mechanical reproduction of sound. It feels like we are finally treating AI like a collaborator instead of just a very complex tape recorder.
It also changes how we build these systems. If you know your downstream LLM is smart enough to handle a bit of noise or a missing "the," you can lean into the speed of a TDT or a CTC model. You don't need the model to be a perfect poet if its only job is to tell the robot to turn left at the red door. You just need it to be fast enough that the robot doesn't hit the door before it hears the command.
So, if you are a developer listening to this, and you are trying to figure out which of these three pillars to lean on for your project, how do you choose? Because it feels like the lines are blurring. We have UniASR doing both streaming and batch, and we have TDT getting smarter.
It really comes down to the latency to context ratio. If you are building something that requires immediate sub-second feedback, like a voice-controlled game, a real-time translation earpiece, or an industrial robot, you have to look at transducers, specifically the new TDT models like Parakeet V2. The efficiency of skipping those blank frames is just too good to ignore. You are getting the smarts of a language model with the speed of a streaming engine.
And if you are doing long-form analysis, if you are transcribing a board meeting, a legal deposition, or a 3-hour podcast episode,
then you go with the encoder-decoder path, but you look at these new unified models like Vibe Voice. The ability to handle 60 minutes of audio without breaking it into chunks is a game changer for accuracy. When you chunk audio into 30-second bits, you often lose context at the boundaries. A speaker might get cut off mid-sentence, and the model loses the thread of who was talking or what the subject was. Unified models solve that by keeping the entire conversation in their active memory.
what about the Speed King? CTC? Is there still a place for it? Or is it going the way of the dinosaur now that transducers are getting faster and more accurate?
CTC is still the go-to for high-throughput infrastructure. If you are a company like YouTube or a massive call center and you need to transcribe millions of hours of audio for indexing and search, the real-time factor of 2000 plus that you get from CTC is unbeatable from a cost perspective. You can run those models on much cheaper hardware and still get good enough results for search and discovery. It is the workhorse of the backend.
It is interesting that even in 2026, the old architecture from 20 years ago is still the workhorse for the big data stuff. It just goes to show that newer isn't always better for every scale.
And we shouldn't forget the conformer layer, which is the other piece of this puzzle. Whether you are using CTC, a transducer, or an encoder-decoder, almost all of them are now using conformer blocks. This was another breakthrough where researchers combined convolutional neural networks, which are great at picking up local patterns like individual speech sounds, with transformers, which are great at global context. It is the engine inside all three pillars.
So the pillars are the different ways the house is laid out, but the bricks are all essentially the same, conformers at this point.
For the most part, yes. But the layout determines how the data flows. I think what is most exciting about this month specifically is that we are finally seeing the streaming gap close. For the last few years, there was always this unspoken rule in the industry. If it is streaming, it is going to be at least 15% less accurate than if it is batch processed. But with TDT and the new SELM hybrids like Canary Quinn, that gap is shrinking to maybe 3 or 4%.
That is the point where most humans won't even notice the difference. Which brings us to the bigger question, does automatic speech recognition even exist as a separate field by this time next year? Or is it just a feature of the multimodal LLM?
That is the big debate in the labs right now. I suspect that by 2027, we won't be buying an ASR model. We will just be interacting with a multimodal model that has a native audio interface. The idea of transcribing audio into text just so a computer can read it is actually a very 2024 way of thinking. A truly intelligent system should just understand the audio directly, including the sarcasm, the whispers, and the background environment.
It is like how we don't transcribe what people say into a mental notepad before we understand them. We just hear the meaning. The text is almost a byproduct. If you need a transcript, the AI can generate one, but it doesn't need the transcript to know what you want.
That is the direction the research is heading. If you look at the Moshi model from Qt, it is a glimpse into that future. It is a bit messy right now, and it can hallucinate sounds just like an LLM can hallucinate facts, but the vibe is that it is a single, unified brain. It is not a chain of models, it is one intelligence that happens to have ears and a voice.
I love that we are using vibe as a technical term now. It feels appropriate for an era where the machines are finally learning how to listen to the nuances of human speech. We are moving from, what did they say, to, what did they mean?
It is not just the words, it is the prosody, the emotion, the hesitation. A standard ASR model might give you the words, but a psalm or a full duplex model like Moshi can tell if you are angry, confused, or lying. That is where the real intelligence lives. We are finally capturing the data that was previously lost in the conversion from sound to text.
Well, I think we have given the folks plenty to chew on. If you are building in this space, the takeaway is clear. Stop obsessing over raw word error rate and start looking at the latency to context balance. If you need speed, look at TDT. If you need depth, look at the new unified encoder. Decoders. And whatever you do, stop making people hold their phones like a slice of pizza.
The digital sandwich must die, corn. I think we are finally seeing the tools that will kill it. We are moving toward a world where technology is invisible and the interface is just natural conversation.
I'm ready for it. I'm tired of shouting at my cursor and waiting for it to catch up. Before we wrap up, I want to give a quick shout out to our producer Hilbert Flumingtop for keeping the gears turning behind the scenes and making sure we don't have any latency issues of our own.
And a big thanks to Modal for providing the GPU credits that power our research and the generation of this show. We couldn't do these deep dives into the engine room of AI without that kind of compute.
This has been my Weird Prompts. If you enjoyed this dive into the technical pillars of ASR, we actually covered the broader context of inference speed back in episode 1479, The Speed of Thought. It is a great companion piece to this one if you want to understand how the hardware side of this is evolving alongside the architectures. We also talked about the early frustrations of voice tech in episode 1218, The Digital Sandwich, if you want a trip down memory lane.
You can find all of our past episodes and the full archive at myweirdprompts.com. We are also on Spotify, Apple Podcasts, and pretty much everywhere else you might be listening.
If you want to get notified the second a new episode drops, search for My Weird Prompts on Telegram. We post the updates there as soon as they are live.
Thanks for joining us in the engine room today. We will be back soon with more weird prompts and deep dives into the tech that is changing our world.
See ya.
Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts. in mind.